In this example, we have two protons. They're separated by a femtometer, and a third proton is slowly, that word slowly is really important, is slowly brought in from infinity and placed at rest at point P, so at the top of this triangle. Where it says slowly, we're going to assume that means it moves at a speed of about 0. Okay, so now we understand the situation. Oh, and then it's placed at rest at point P. V equals 0. Okay, find the change in electric potential energy of the system as the third proton is brought in. So it starts very far away, it's brought in. If we want to find the change in electric potential energy, we're trying to find delta U equals U final, subtract U initial. Let's find our initial first. Initially, the third proton is very far away. So U initial is just Q1 and Q2. So it's just the two protons. So the initial electric potential energy is K times the charge of the first proton times the charge of the second proton divided by the distance between them squared. So the distance between them is labeled D in this picture. Oh, not distance squared, just D, sorry. So 8.99 times 10 to the 9 newtons meters squared over coulombs squared times 1.60 times 10 to the minus 19 coulombs. That's got to be squared because I've got one proton times the other proton, divided by D, which is 10 to the minus 15 meters, gives me an initial electric potential energy of 2.30 times 10 to the minus 13 joules. Okay, what about my final potential energy? So UF is all three protons. So I've got Q3, I could label them Q1, 2, and 3, I suppose, if we wanted to. Q3 is a proton, Q1 is a proton, and Q2 is a proton. So our total final electric potential energy, UF equals U total. So we need all the different combinations. So U between 1 and 2, so our first two protons, we already have that value, plus between 1 and 3, plus between 2 and 3. The distance from here, let's see how we're going to find these. Okay, so let's write down U12 first. We already know that one. U12 is 2.30 times 10 to the minus 13 joules. U13 is going to be K times charge 1, that's a proton, times charge 3, that's a proton, divided by the distance between 1 and 3. Let's make sure we understand what the distances are. The distance between 1 and 3 is from here to here. This is not a number we know just yet. We do know that the height of the triangle is 10 to the minus 15 meters. So from here to here is D. From one proton to the midpoint is a half of D. So between two protons is the full D. From one proton to the middle, which is where that line drops down from, would be a half of D. So this distance would be D divided by 2. So D13 is something we can find. That's the hypotenuse of a right angle triangle. D13 is the square root of this side squared, D over 2 squared, plus this side squared, D squared. Let's see, D over 2 squared is D squared over 4. D squared over 4 plus D squared is 5D squared over 4. Got to take the square root there. And then when we do the math, root 5D over 2 is going to be this distance right here. And you could do that on your calculator if you wanted to, no problem if you prefer it that way. So let's go back to our calculation for the potential energy between 1 and 3. So K times E squared divided by D13. D13 is root 5D over 2. I think I won't write in all my numbers here, it's just my slide's getting a little bit full. And for my next one, U23, U23 is exactly the same as U13. So we're the same distance away, we're the same size of the charge. And then if we do this on the calculator and add up to get our total electric potential energy, so we'll do this number on the calculator and do this on the calculator, add them all up, and what we get is 6.418 times 10 to the minus 13 joules. So that's our total electric potential energy. And then we're asked to find the change in potential energy. So delta U equals UF minus UI. Let's put those numbers in. 6.418 times 10 to the minus 13. Subtract 2.30 times 10 to the minus 13. Gives us a change in electric potential energy of 4.118 times 10 to the minus 13 joules. Okay, there's part A. Find the change in the electric potential energy as that charge is brought in from very far away to point P. The next part, what is the work done by the electric field as the proton is brought in from infinity? So here's where we remember the relationship between work and potential energy. Work done by the electric field. I'm going to use some subscripts here now because we want to think carefully about what does what. So the work done by our internal force, the electric force or the electric field, the work done by the electric field is minus delta U equals minus 4.118 times 10 to the minus 13 joules. Okay, there's that work. Let's also remember from our work energy theorem from Physics 1020 or 1050 that the total work done on the system is equal to the change in kinetic energy of the system. But the change in kinetic energy of this system is equal to 0. So initially the two charges were still. This guy is moving slowly, i.e. it has a speed of 0, and at the end it has a speed of 0. So the initial speeds are all 0, the final speeds are 0. Delta K is just 0. So what does it mean if the total work done is 0, but the work done by the electric force was negative? Well, when we say W net, the net work done by all the forces means we have to add up the work done by the electric force to any work done by any external forces, perhaps somebody is pushing. So that has to be equal to 0. It means that the work done by the external force is negative the work done by the electric force. So that's going to be plus 4.118 times 10 to the minus 13 joules. That the work done by the electric force is negative means that the electric force and the displacement were in opposite directions, okay? It did not move this way naturally. So if the force and the displacement were in opposite directions, that electric force didn't bring that charge into place. It was repelled by it the whole time. So that's why the work done by the electric force is negative. So the electric force was repelling it, but it was pulled inwards. So if it was pulled inwards, then something had to pull it inwards. The something that pulled it in was some sort of external force or a pushing force. And that work is positive because it was pushed inwards and it moved inwards. So just kind of a quick summary then. We'll say that we had to have an external force which had to push the proton into